Students, today we are going to learn about the Coriolis effect, what that is, and how the rotation of the Earth affects weather patterns. This demonstration is intended to go with the lab sheet, so you'll be working alongside with me in this demonstration. So the first thing we want to do is explore a little. I have an old-fashioned turntable, a record player here. I'm not going to be using this part for the record. I've put a piece of paper on the turntable and I'm just going to make some observations. So I'm going to put a pen right near the center and observe it moving around. And now I'm going to try it out here. Ooh, it seems to go really fast. So out here, my pen seems to be moving very quickly on the page, and if I put it in here, it seems to be moving more slowly. You can even hear it maybe in the video, how much louder it is on the outside because it's moving so much more quickly. So let's look at the paper. So we know that each of these circles was made in the same amount of time because the circle is revolving and the rate of revolution is the same, right? So whether you're on the inside, it makes one circle. It's about 2 seconds, I would say. Let's try it. Ready? 1, 2. Let's try it out here. 1, 2. Yep, it comes back to the start in about 2. So the rate of revolution is the same. The part on the inside is small and the part on the outside is large. So if the rate is the same, the time passed is the same, then we have a much greater distance going around here and a smaller distance there. So what would that mean for the speed with which we're going around? So we can see that this is going much more quickly and that's going more slowly. So for number 1, it says if the time is the same, compare the speed of the pen moving on the paper to make the circle. So you'll want to keep in mind that speed is distance over time. So for the time, if the time of one revolution is the same, then the distance is much greater. This pen goes all the way around and this one goes just a small distance. So if the distance is greater or smaller and the time is the same, what does that mean about the speed? So take a second to write your sentence there in number 1. The next step, we're going to put a spot near the center and a spot near the edge. And let's see how the speed that these spots move around compares, and we'll see if you are on the right track from number 1. Take a look. How do the speeds of the 2 dots compare to one another? Take a look at the outside dot. If your eyes are trying to follow it, it's having to move very quickly. If your eyes are following the one on the inside, it's not moving as quickly. So the dot closer to the center is moving more slowly than the one near the outside. Now let's imagine that we are looking at a globe that looks similar to our turntable. So if this in the center were the pole coming through and we were rotating around looking down from the top of the North Pole, then what places on the globe would be moving more quickly around the axis? So I'm going to transfer over here. We're actually going to look at this globe from the top. So this is the North Pole. If it's rotating like this, in the similar way, if we're looking directly down from the top, it looks a lot like that turntable, doesn't it? So a spot here at the North Pole, near the North Pole, would be moving. Think about the speed of something near the North Pole in a single day compared to the speed that something is moving near the equator in a single day. The circle that a spot on the equator is making in a single day is a much larger circle, but it still only takes 24 hours. A spot near the pole still is only going to make one rotation in 24 hours, but it's actually moving a lot more slowly than a spot near the pole. I've now turned my paper over and I'm going to turn on the turntable. Now what I'm going to do is I'm going to start with my pen and I'm going to put it near the center and pull it directly towards me. I'm sitting right over here. I'm going to pull it in a straight line towards me like this. I'm just pulling it straight toward my nose. If I do it more slowly. Now let's take a look at my lines. Now, I was moving my pen in a straight line. I was moving it straight like that, but look at the patterns that are on my paper. Let's see which direction was the line deflected. So if I'm traveling along the line, I went from inside to outside, so I'm going to draw some arrows on here and line it up from your perspective. So straight ahead, which direction was my line deflected? To the right or to the left? It's deflected to the left, isn't it? It's deflected counterclockwise. Now, I'm going to use a different color. And I'm going to start from the outside and I'm going to move straight towards the center. Here I go. Now let's see what I've got. Now remember, I'm going from the outside to the inside, so I'm going to again draw an arrow on these lines to get a sense of what direction I was moving. Now, imagine you're moving along this line right here. Which direction is it deflected? Again, it's deflected counterclockwise, isn't it? So our turntable is moving clockwise, and all of our lines, whether they were going toward the inside or toward the outside, were deflected counterclockwise. Now, if we're looking at the Earth, from the perspective of the North Pole, the Earth spins counterclockwise. If we're looking at it from the North Pole, it's spinning counterclockwise. But if we take it and we look from the perspective, I'm going to keep it going, perspective of the South Pole, can you see that it's actually spinning clockwise? So depending on the perspective that we have, from the South Pole, it's spinning clockwise. From the North Pole, it's spinning counterclockwise. So let's look now at the steps in our lab. As we observe our lines from the turntable, we want to think about what the arrows tell us. So which direction was the line deflected? In both cases, it was counterclockwise. Right? I'm just going to circle it, counterclockwise. And then when we went in the other direction, that was from the inside out. When we went from the outside in, remember as we went along this way, we were again curving to the left or counterclockwise. So either way, whether we were going in or out, they were the same. So I'm going to put this in a complete sentence. The curve was in the same direction while moving toward the pole, I'm going to call it, or away. So our turntable was moving clockwise, and the lines were deflected counterclockwise. So they're going the opposite way, right? So from the perspective of the South Pole, the Earth spins clockwise. So in the southern hemisphere, we would expect, like we saw on this model, for things to be deflected counterclockwise. But in the northern hemisphere, we are spinning counterclockwise from that perspective. And so then in the northern hemisphere, we would expect to see things deflected in the opposite direction. And indeed we do. We see things deflected clockwise in the northern hemisphere. Now, why is this? We're going to take a look at that as well. It's because the person on the near the pole is moving more slowly than the person near the equator. So we'll get to that a little bit. The Coriolis effect is what this is called, this curvature. It's caused by an imaginary force that has very real effects on weather and the Earth, on Earth and also on other planets. The Earth spins counterclockwise as viewed from above its north pole. Objects are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. Now, the deflection is only apparent on Earth. However, an observer watching from space would see the object's path as a straight line. Just like from the perspective of the turntable, when I was drawing the line toward me, I could see my hand moving directly toward me. It's just the line it created on the spinning paper was curved. It's because we are viewing in the frame of reference of the rotating Earth that we see this apparent deflection. So now let's apply this a little bit. If you were on an airplane that takes off from Miami and you were flying to Toronto, Canada, would your plane be deflected to the left or to the right as it flew? Now this is in the northern hemisphere. So which direction do things deflect in the northern hemisphere? I can go back up here and realize that it will be deflected clockwise. Now take what you understand about that and continue on with the next section where you are looking at some patterns that show wind patterns on the surface of Mars. So take a look at that and see if you can use your understanding with your group or on your own to answer the questions.